Hello, those of y'all at home. You need a periodic table out, so get out a periodic table. Also, all of the people in class have copied down this screen, so pause the video and copy it down. All right, y'all, brand new stuff. Very beginning of a unit, so stay on top of your game. Don't fall behind. Oh, and please put away all electronics. Y'all have electronics out. Put them away so I don't come take them from you. Duarte, that's you too, my friend. All the way away. As I very briefly yesterday mentioned, Unit 4 is a more in-depth look at the periodic table. Today, our focus is going to be why location on the table creates ions. And then on Friday, we're going to really dig into the anatomy of the table to figure out that there's a lot more than just symbols and numbers. The specific locations of the squares and the way that it's shaped can tell you a ton about the table. So more on that later, but let's start today by revisiting valence electrons. If you remember, last unit, anytime I asked you to find valence electrons, what did you do? You looked at the notation, you found the highest energy, right? You look at a notation and you find the biggest big number, which is the energy levels, and you would count up all of the electrons in the highest energy. What was the range? The number of valence electrons could only be a number what through what? 8 was the max, right? So it was always 1 through 8 in regards to how many valence electrons an atom could have. Well, I need you to be able to count valence electrons much faster than that. You're going to see moving forward that valence counts are surprisingly important for a bunch of other things. So I want to train you on a cheat on how to count valence electrons without writing a notation. So here's what I want you to do. In your spiral, I want you to draw this periodic shape. Now, y'all leave yourself a lot of room. Leave some room above and room below the shape you're about to draw, because we're going to add a bunch of stuff to it. All right, this is probably a scam call, but it's going to be on this video forever now. Here we go. Hello?
Hi, is this Mr. Cummings?
Yes.
Hi, it's Ms. Johnson from Jordan. You called about a yearbook. What grade is your daughter in now?
She is now at Dobie, so she's in 7th grade now. Yes. No, I'm actually teaching, but I can take down no, you're good, but I can take down an address. Okay. All right. All right, I'll send her an email. Thank you. It wasn't a scam. Hooray. Anyway, blah, blah, blah. So draw this shape prettily, because we're going to use it during the entire lecture. Here we go. It's basically an outline of the table. Not only am I drawing the outline of the table, I'm going to draw the column numbers, which look like this. Look at your real table. Do you see where those blue numbers are coming from? Look at your table. Do you see those are the column numbers? Now, they're really called group numbers. That vocab word will be on your slides on Friday, so you don't have to write it yet. but I'm going to call them what they're called. So instead of calling them columns, I'm going to call those groups. Anyway, there are 18 groups on the table. Make sure you can see that on your table. We can use these group numbers to cheat on the valence electrons. And here's the way it works. All of the elements in group 1 have 1 valence electron. And all of the elements in group 2 have 2 valence electrons. This cheat does not work for groups 3 through 12. There's a different rule for them that we're going to talk about Friday. What's the maximum valence number you can have? 8. So don't tell yourself, oh, well, 13 must have 13, because that doesn't work. How many do you think 13 has? 3. And then it just counts straight up. Why can't you know where you were at, dude? Where you were at. I'd love to sit next to you in church, see what that's like. These valence electron counts apply to all of the elements in that entire column. So I'm not showing you anything new. This isn't like, oh, this is way different than last unit. No. You could have done this for electron configurations. I just didn't teach it to you because I wanted you to practice your notations. But this is true for all of the elements in the column. So if that's the case, I handed out a sheet with questions on it. Those of y'all at home, it looks like this. I just handed it out so you don't have to copy down my questions. So we'll be going through these during the period. But anyway, the first question on that sheet says, how many valence electrons does barium have? Well, look. Barium lives right down here. Now, last unit, if I would have asked that, you would have said, well, I got to find me a notation, and then I'll count up the highest electron energies and blah, blah. But how many does he have? 2. And it'd give you the same answer if you did the notation. But now you can do it quickly. Let's get Aspen to play 3, 4. All right. Let's look at another question. It says, how many valence electrons do not answer does tellurium have? Let's go over to cluster 1 and talk to seat 1. Hey, 1-1, what's your guess on tellurium? How many valence electrons do you think tellurium has? So she said 6. Agree or disagree? Agree, because all of the elements in group 16 have 6 valence electrons. I'm sorry? Where's there another TE? Oh no, that's TC. It's technetium. Anyway, so we can now count valence electrons quickly and easily, yes? Okay. The main thing that I want us to do today is look at ionization. Now, we've talked about the word ion before, right? During Unit 2, we said that an ion is any charged atom. Remember the marbles? All right? We know that anytime the protons and electrons, the positives and the negatives, don't equal each other, if they're off, meaning the electrons have changed, then you have an ion. There's a charge, positive or negative, depending on if electrons were gained or lost. So that was the definition of ion. So you know what the what is. The focus of today is I want you to know the why. Why would it happen? Why would an atom decide that they need to gain or lose electrons based on locations on the periodic table? So the process of gaining a charge is called ionization, as you already wrote down. Before we get into the why, there's some secondary vocab that comes with being an ion. So check it out underneath ionization. We have vocab words for positive and negative. So I would like somebody or all of y'all to pronounce that word. Say it. All right, cation is wrong. Try again. Cation, not right. Try again. Cation, still stupid. Yeah, it is a positively charged ion is a cation. Pronounced cation. Don't say it any other way. All right? So if you have less electrons than protons, it would be positive, and we would describe that as a cation. Now, a negatively charged is a dog ion, which is not true, but it would be more fun if it was. It's an anion, which you're pretty used to an A or an an being in front of a word meaning negative. So anions are negative. While you usually don't have an issue differentiating the general definitions, you do get confused on gaining or losing electrons. The reason you get so confused here is because you're used to if something is negative, an anion, that means that that thing has lost something. Like if I were to tell you that your bank account is in the negative, you would probably assume it's because you lost money, in which case you're correct. But the reason this confuses you is it's kind of opposite, because the particles we're talking about are negative. If you're losing negatives, that makes you positive if you think about some general algebraic rules. But yeah, like if I were to take all of Landon's negativity away from him, he would be losing electrons. It would leave him finally more positive. All right, so your slide differentiates between that, but cations, all right, remember they all start stable. Cations have lost electrons, making them positive because now there's more protons. Anions have gained electrons, making them more negative because electrons are negative. So with that in mind, why does this happen? All right, the first thing that I need you to know is kind of abstract, but I want you don't even have to write this down. I just want you to imagine this number line. You don't even have to write it down. I just want you to, we're just going to consider it. All I've done is I've counted down from 8. 8, 7, 6, 5, 4, 3, 2, 1. 8. Why'd you let me put it on?
I know what you're doing. Oh, I know.
Come on, get angry. Anyway, 8, 7, 6, 5, 4, 3, 2, 1. 8, 7, 6, 5, 4, 3, 2, 1. 8. Man, I was good at this last period. Anyway, I want you to imagine counting down from 8 an infinite number of times. If that's true, all right, and you look at this number 8, what two numbers is it always surrounded by? It's always surrounded by a 1 and a 7. Now I know this sounds really weird, but I'm going to reference this idea in a moment. But just imagine an endless countdown of 8 to 1, in which case the 8 is always surrounded by the 1 and the 7. Now, the reason that the 8 is so important is because if you look at your slide, the rule that's going to be in charge of deciding, well, is an atom going to gain or lose electrons, is the octet rule. Not only is 8 the maximum number of valence electrons you can have, it's the magical number. All of the elements on the periodic table, all of them on the entire table, want 8 valence electrons. How many of them have 8 valence electrons? A small amount or a large amount? A super small amount. What's the name of the group that has 8 valence? Remember, you know the names of the noble gases because it was one of your notations last unit. Y'all, there are only 6/7-ish elements on the table that already have an octet. We refer to them as the stable elements because they're the only happy ones. What that means is all of these other elements want to get to 8 in whatever way is possible. And that's why ions form. Because 95% of the table doesn't have 8, so they're going to move their electrons around to get to 8. And I want to show you how they do it. In order for us to do this, I'm going to write down all of the elements in the second row, and I want you to do it with me. All right, so the second row is made up of lithium, beryllium, I'm going to skip 3 through 12, boron, carbon, nitrogen, oxygen, fluorine, and neon. So there's the whole second row. Next, I want to draw their Lewis structures. Ooh, their Lewis structures. Is that going to take us a long time, or is it really easy?
I don't understand.
Way to go. It's really easy because remember, it's a dot for every valence. And now that you know how to quickly know how many valence there is, you can quickly put the dots. So how many dots does lithium get? One, because he's got one valence. How many dots does beryllium get? Two, because he's got two valence. And then do all of the others. Part of my personality. The number of dots in each Lewis structure perfectly matches the valence count that is found in each of the columns. So why do the electrons, or rather, why do the atoms move their electrons? So let's start over here with lithium. Here's what's true. Atoms can always either gain or lose electrons to get to 8. They're always going to pick whichever is easiest, whichever requires the least amount of energy in nature. So look at lithium. Now, here's where I want you to think about that endless sequence of 8, 7, 6, 5, 4, 3, 2, 1s. We're at the 1, all right? So in order for this 1 to become an 8, how many dots would lithium have to gain to get to 8? He'd have to gain 7. How many would he have to lose to get to 8? He would have to lose 1, right? Because remember, it goes 7, 8, 1, 2, 3, 4. So from the 1, you could just lose a single electron to get to 8. If you don't like thinking about it that way, then just think about 0 being as good as 8. All right, 8 is the perfect number, or 0. So lithium could gain 7 dots or lose 1 dot. Which do you think is easier to do? The smaller number. Between 1 and 7, pick 1. So you just said that lithium wants to lose 1 electron. What would the resulting charge be if you lose an electron? Now, in case you can't see that, because there's always 5 students in the room that are endlessly confused on this, don't write this. But if you were to look at lithium's nucleus, or rather his atomic structure, he's got 3 protons, right? He's element number 3. Lithium's got 3 protons, which means on the table, he's got 3 electrons, because we know the protons and the electrons are equal to each other. But we just said to become stable, to hit his octet, that lithium wants to lose an electron. And if you lose one of those electrons, the resulting charge is positive 1. I'm going to write that up here. Positive 1. Which is characteristic of the entire column. Look at beryllium. Beryllium has 2 choices, because there's always 2 choices. You can gain or lose. How many electrons does beryllium have to gain to get to 8? he would need 6 more dots, 6 more electrons. How many does he have to lose to become stable? 2. Smaller number wins, so I picked 2. So beryllium is going to lose 2 electrons. What will the resulting charge be if you lose 2 negatives? It will leave you positive. So group 2 is plus 2. Now again, this ionization trick does not work for those dudes, so we are not worried about them till Friday. Let's skip over to nitrogen. Look at nitrogen. He's in group 15, all right, with 5 valence electrons. That's why there's 5 dots. Let's talk about his choices. How many dots does he have to gain to get to 8? 3, because he's at 5 right now. How many does he have to lose to get to stable? He would have to lose all 5. What's he going to do? Nitrogen, you said, wants to gain 3 electrons. What will the resulting charge be if you start neutral, but you gain 3 negative particles? -3. Try to fill in the rest. Take a minute and try to fill in the missing black numbers at the very top. There's a couple that might confuse you. Just do your best. It's fine. I'll give you a moment.
That doesn't make any sense. No, what about the next
I'm
one?
going to explain it then. I know that carbon confuses y'all. Hang tight, I'll explain it. Do the others if you don't like carbon.
You can either add or subtract, right? Because it's going to be the same. Depends on what you want it to be a positive or a negative.
All right, let's go talk to some people. Let's go over to cluster 2. Cluster 2, seat 5. Hey, 2-5. What did you decide that boron wants to do? Gain or lose? He said lose 3 electrons. Anybody, what will the resulting charge be? +3. Yeah? All right, let's go somewhere else. Let's go over to cluster 1 and talk to seat 6. Hey, 1-6. What do you think oxygen wants to do? Gain 2. I agree. Anybody, what's the resulting charge if you gain 2? -2. I'm going to fill in the others because you're not asking questions and I don't want to bore you. So, fluorine then is going to gain 1 to get to 8. If fluorine gains 1, he'll have a charge of -1. The noble gases are the only group that's already stable, so they will not let you touch their electrons. They don't gain or lose. They're already happy. And then carbon he's technically +4, -4. However, we don't really cover that at any point in this class. So you can write it if you want to, but it's more info than you need. because he can gain or lose 4, and it depends on what is happening with compounds that he's forming. So while that's true, I am ignoring it. Y'all, this process is called ionization, the process by which the atoms gain a charge because they're moving their electrons around to become stable, to hit the octet. These predicted charges that you've written are true for the entire group. So I can ask you about any element in the column, and they have that charge because of this reason, right? These guys are just representatives. So if you look at fluorine, well, it turns out that iodine acts the exact same way because he also has 7 valence. He also wants to gain 1, so he'll also be -1 when he does it. Yes. It does, but those man-made elements at the very bottom are never covered. We don't even talk about those in AP. So here's what I want you to do. On your real table right now, I want you to write down these oxidation states in the proper location. Again, on your real table, write down the +1, +2, +3, -3, -2, -1 above the proper groups. Not only am I having you write these right now, y'all, you should write these anytime you get a new table. All right, it's going to blow your mind how often the oxidation states, by the way, they're called oxidation states. You wrote that vocab word on the opening slide. But you'll be surprised how often you need to know them. So if you're one of the people that I'm always handing out new tables to, because you don't know how to put your electronics away either, then be in the habit of writing the oxidation states, or like especially on test day, right? On test day, when you pick up a table, sit down, put your notes away, and then write down your oxidation states because of the amount that they can help. So let's go back to our question page that I handed out to you, and let's see if we can answer some of these questions. Let's draw some cards. Let's go over to cluster 1, seat 2. Hey, 1, 2, what vocab word from a little bit earlier in the lecture describes calcium +2? Look on the opening slide, a vocab word, Ca+2. So look at his charge. What's calcium's charge in my example? Positive. So what vocab word describes positive ions? Come on, I know you wrote it. Oh, yeah, see, positive ions. Yeah, a cation. All right. And look, why did I put Ca+2? Because calcium lives down here. All right, calcium lives in this area, and calcium is +2. All right, let's do another one. Let's go over to cluster 5 and talk to seat 4. Aspen, it's you. Aspen, where are you? I forgot right there. Oh, there he is. Hey, Aspen, has phosphorus -3 gained or lost electrons? He said lost. Do you agree or disagree? I disagree also, because we know that electrons are negative. So if phosphorus is negative, you've had to have gained electrons. By definition, anions are negative and they have gained electrons. You can pass the burn. All right. Why did I put phosphorus -3 in my example? Because phosphorus lives in this area. Phosphorus has a charge, an oxidation state of -3. Let's keep going. Let's go to cluster 6, C3. Hey, 6-3. What is the oxidation state of hydrogen? +1 is correct. Hydrogen lives over here, therefore his charge is +1. Let's go another. Let's go to cluster 2. C4. Hey, 2, 4. What is the predicted charge of sulfur? -2. Because sulfur lives right below oxygen. Therefore, just like oxygen, oxidation state of -2. Easy. I have one more point to make. I'm sorry, and it requires you to write. The last thing I need you to do is start by copying that. I'll show you. Copy that. Pause. Oh, look, it's a class. That's true. That's right. I chastised you. Dang it.
Do they hear me if I'm talking right now?
Usually not. It's not very good about behind the system audio.
But if I talk,
Talk loudly.
I don't ever talk loud. Oh, give me, I want to hear it. I never talk. You're so happy to make me laugh. So you started getting me to do that. I'm just not doing anything, you started talking. I think my hand on my
The final thing I need you to be able to do today is very, very simple. I need you to be able to name ions. Like if we were having a conversation about hydrogen, and we were like, oh, well, this is a charged hydrogen. Well, he has a certain name when they have a charge. So these rules help you go through it. So let's take a look. If an atom has lost electrons and become positive, then we name him, well, super simply, this is like a kindergarten rule. To name a positively charged ion, you're going to say the name of the element, and then in a separate word, the word ion. So it would be hydrogen ion, because he's positive. That one's pretty simple. It's the anions, the dudes that have gained electrons and become negative, that you have to actually think. Well, first off, when naming anions, you don't say the word ion. You can, but it's redundant. It's not technically wrong. But you can do it in one word. And what you do is if it's one of these guys, this is where the anions live, right? The negative guys. Then the suffix of the word, the end of the word, changes to "ide." Well, it would never be hydrogen, though, because hydrogen's positive. But let's look at a couple examples. All right, let's take a look at sodium. All right, now sodium is usually neutral. Keep in mind, these elements all start with no charge. But if sodium were to undergo ionization, I would say, well, sodium lives in this area. Therefore, sodium's charge is +1. So what would we call him? A sodium ion. All right? Not sodiide, all right, because you don't add "ide" to the end of cations. And it's 2 words. Don't call him a sodium ion. All right? It's sodium ion. All right, let's do another one. What if I wanted us to name phosphorus? What if phosphorus was becoming an ion? Well, phosphorus is an anion because he's in a negative column. So I can't call him a phosphorus ion. That would be wrong. What do you think? Phosphide. He would be phosphide. Now, if I was quizzing you and you called him phosphoricide, It's wrong, but I would give you full credit because it takes a little bit of time to figure out exactly where to slide the ide. I like it when I run. So whatever, but over the next couple months, you're going to start to really feel out where the ides go. So let's see if you've listened. I want you to do those last two on the screen. We already did the first two on the screen. Do the last two. It's aluminum and iodine. Right now, they're writing the ion forms of aluminum and iodine. Follow the rules. We'll draw cards. Element 53. What is aluminum charge?
No, we were just like.
Oh, you're just inventing things. All right. I'm the only god in the room. Let's see how you did. Let's go over to cluster 6. C4. 6-4. What do you think about aluminum if he had a charge? What would you call him? He would be a cation. You're right. He's absolutely a cation. So what would you call him then if you followed the cation rules? All right, he is positive. So following the rules, it's the name of the element, which is aluminum, and then the word ion. So aluminum ion. Not aluminide. There's no such thing. Aluminum ion. Let's do the last one. Let's go over to cluster 1 and talk to C4. Aspen, we found you. Aspen, what do you think iodine is as an ion? Don't be whispering to his back of his head. All right, so let's do it together. All right, iodine lives down here. So iodine has a predicted negative charge, making him negative. So follow the anion rules. So give it a shot. Think about if you jumped out of an airplane without a parachute. How would you describe what happened? Iodide, right? All right, it's not iodine and it's not iodine ion, right? You change the end to ide, so iodide. Lab tomorrow.